in liquid form. Now Eric's going to talk about the general arrangement.
Here we have the outboard profile of the ship, and as you can see, the cargo deck is 190 meters long. To give you an idea how big that actually is, we can fit the entire Superdome on top of our cargo deck. We're going to start with the inside of the main deck. Here we allowed storage for the lashing and cargo equipment, as well as port and starboard storage for the oak cribbing, and also storage for the liquid product manifold and 2 forklifts. Here we have the O1 deck. This is where we have our hospital, as well as the inner gas and exhaust gas cleaning system that Adam talked about earlier. Our O2 and O3 decks are what we consider our recreational decks. The sole purpose of these 2 decks is to raise crew and client morale by providing entertainment and a means by which they can maintain personal health while at sea. Our O4 deck is basically our machinery and workshop area. On this deck we have our workshop, spare parts room, computer room, machinery library that contains any records of any machinery or equipment on board. Here we have our O5 deck or forecastle deck. Primarily this deck's made up of the galley and mess area. You can also see a conference room for the officers that overlooks the cargo deck. Here we have the O6 deck. This is the main accommodations block for the ship's crew and lower level officers. All these cabins were sized using ABS Habitability Plus criteria. Cabins on this deck were provided for a total of 38 people, ranging from stewards and regular deckhands to some lower level officers and mates. Also housed on this deck are the emergency generator room and cargo control room. Here we have the O7 deck. This is the main accommodations block for the ship's upper level officers and distinguished guests. For this deck, cabins were provided for a total of 17 people, bringing our total berthing to 55. And as you can see, there's a large space designated for the HVAC room located forward. Here we have our bridge deck and O9 deck. House controls were located forward and aft to allow for easier operation and maneuvering of the ship. Also notice the open deck around the house that was incorporated for better visibility around the house at all angles, and also wing decks that extend out to the furthest extent of the ship to allow for over the side visibility. And also on the O9 deck, you'll notice the helipad and its appropriate receptions and communications room. That wraps up the GA. Now I'm going to turn it over to Daniel for stability.
To investigate stability, we set up 5 load cases, 1 of the empty vessel, 2 at the maximum transit draft with a composite cargo or spar on deck, 1 with the deck slightly submerged, and finally a condition at the maximum submerged draft of 31 meters. For this ship to be U.S. flagged, it must adhere to U.S. Coast Guard rules for ships. Our analysis checked intact stability and a 58-knot wind applied on a large cargo sail area. We also checked damage stability using the probabilistic method, according to SOLAS rules. This checks the likelihood of the vessel surviving given various flooding conditions. These criteria only apply to transit cases. This slide presents the 2 resulting curves of maximum allowable vertical center of gravity. The white curve on top represents the intact stability, while the red line on bottom represents probabilistic damage. These curves can show whether a load condition passes or fails stability requirements, and as seen here, our 3 cases all lie on the passing side. These curves can be modified and combined to show the maximum center of gravity of the cargo above the deck, as shown here. The natural roll periods of both the load line and submerged cases were computed as 11.6 and 23 seconds. This figure on the bottom is the linear amplitude responses for the 6 degrees of motion using strip theory analysis in Moses. To minimize motions, these roll periods should be outside the design range of wave periods. 11.6 seconds is lower than the desired value of 16 seconds or higher. Existing vessels of this type are extremely susceptible to roll motions, and we have recently been investigating adding high anti-roll tanks to the vessel to increase the roll period. Using these RAO curves, the maximum expected motions were computed, specifically the roll. At the loaded draft and the 10-meter beam wave, the vessel will roll only 9 degrees. For a 1/1000th occurrence wave, this maximum response is completely reasonable considering our worldwide operations from Dubai to Brazil. Next, the stability while submerged was checked. Because there are no specific classification rules for stability here, we imposed our own criteria and analyzed the maximum motions expected while submerged. Specifically, the vessel must maintain a positive GM and a roll of less than 1 degree while submerged. To expand our waterplane area with the main deck underwater, 2 aft buoyancy boxes were added to give the vessel added stability and to reduce roll motions. In most large lifts, the cargo will provide some added buoyancy. This slide shows the KM curve without the deck cargo buoyancy, and here we can see the benefit of utilizing the buoyancy of the cargo. The KM curve jumps dramatically at the point of main deck submergence. Conservatively, we considered adding no buoyancy from the cargo, and roll was calculated for the submerged condition. Understanding that submersion will only occur in a controlled environment of half-meter seas or less and less than 15 knot winds, the maximum roll is 0.1 degrees with a positive GM of 2.7 meters. This slide shows what the vessel will look like with its main deck underwater. This case of deck submergence was checked without considering any contribution of buoyancy from the cargo. The case of a typical spar lift of 30,000 metric tons at 18 meters above the deck maintains a positive GM of 0.75 meters, which passes our criteria. This analysis is checked at an even keel. For heavier lifts, additional buoyancy boxes may be added on deck, and aft trim of up to 3 degrees could also be used. Next, Brett will show you our structural design and weight estimate.
Shown here is a typical transverse web frame and transverse bulkhead. All the structures were designed as per ABS steel vessel rules. For the design, a frame spacing of 3 meters and a longitudinal stiffener spacing of 0.75 meters was chosen. All of the member sizing was driven by the large hydrostatic pressures experienced at full submersion of 31 meters. Displayed in this image is the structural layout of main deck. Due to the nature of the operation of our vessel, it is possible that main deck will experience large concentrated loads due to the blocking arrangements to support the payload. Our deck was sized to handle 27.6 metric tons per meter squared, which is the strongest in our class. This image shows the same view as before with the longitudinals removed. This gives a better understanding of the structural layout of our vessel. Shown here is the bulkhead 18 meters off centerline as well as the centerline bulkhead. Notice you can see the longitudinals, the horizontal stringers, and the transverse bulkheads which define our tanks. Due to the length and operation of our vessel, it was necessary to check the longitudinal strength. Shown here is the combined still water and wave bending moment for our ship. As shown, the combined moment for a max lift of 82,500 tons fell below the maximum allowable bending set by ABS. This ensures we pass for a worst case scenario. After sizing and laying out the structures, the weight estimate was completed. The analysis of the weight estimate was done using the Swiss group system, which was broken down into the categories shown in this pie chart. To calculate the weight of the structures, we started by calculating the weight of a typical transverse frame. This weight was then distributed across the length of the vessel using sectional area ratios based on the cross-sectional area of the midship section. Once this was done, we added in the weight of the superstructure, machinery, and the margin. The final weight was about 30,000 metric tons with a VCG of 12.2 meters above baseline. Next, I will discuss the cost estimate and feasibility of our ship.
We conducted a cost estimate and feasibility study for 2 scenarios. The first scenario is for building the ship in a shipyard in the United States with a total estimated cost of $538 million. The second scenario is for building the ship in China with a total estimated cost of $488 million. The major reason for the lower cost of building the ship in China is due to having a lower labor cost compared to the United States. The utilization of heavy lift ships today is about 90%. If we assume utilization of 80% and daily earning of $600,000 million,
the ship will be able to generate a total annual